So let's pick up with where we left off last time, talking about epoxide reactions. All right. And just to review what we did last class, I want everybody to take a second and give me the product of this reaction under acidic conditions versus if we carried out the same reaction under basic conditions. All right, so if we look in both of these cases, we're going to be creating a molecule that has these two functional groups. We're going to have an alcohol or a hydroxyl group from my epoxide oxygen, and then my nucleophile will add on to create this ether group, right? But the question is, which of these carbons is going to be attacked by my nucleophile? All right, and what we want to note is that our green carbon here is a primary carbon, and our orange carbon here is a tertiary carbon. And we discussed we have these different regioselectivity concerns depending on our reaction conditions. All right, so under basic conditions, the most accessible carbon is the one that's going to be attacked. Under acidic conditions, that's true with the exception of this preference for tertiary carbons. So my basic nucleophile here, I'm going to attach to that green carbon. All right, so when I do my products, and again, we'll kind of see why this is going to be helpful here today. Whoops. I'm going to draw what's called this saddle horse projection, where I'm kind of looking at this bond flat here. There's my orange carbon and my green carbon. All right, again, under basic conditions, that primary carbon is the one that's going to get attacked by my nucleophile. So I'm going to add on that nucleophile to that green carbon. All right, that means that my other carbon, and I'm going to draw this bond pointed in the opposite direction, my tertiary carbon, will be left with that epoxide oxygen in the form of that hydroxyl group. All right, and now I need to draw on what else was on that tertiary carbon here, those two ethyl groups. Cool. Under acidic conditions, now I'm going to have to attach my nucleophile to my tertiary carbon, to the orange one. So that means that orange carbon is going to have my nucleophile added. Remember, those neutral nucleophiles will lose a hydrogen in the process. All right, so although my alcohol is my nucleophile, it's going to lose that oxygen. And my green carbon is the one with that hydroxyl group from that ring opening reaction. All right, and now again, I want to put in my ethyl groups that were on that orange carbon. All right, so again, we have this regioselectivity. This is a good example of an epoxide where we see that regioselectivity of our ring opening reactions, how it depends on the conditions. Under basic conditions, our nucleophile will be attached to that more accessible primary carbon. Under acidic conditions, my nucleophile will attach to that tertiary carbon. Cool. All right, and we talked about the mechanisms at work here. Remember, under acidic conditions, you shouldn't see any strong base intermediates. Under basic conditions, it's the opposite. You shouldn't see any strong acids. And there are those proton transfer steps that help manage our charges. All right, cool. So we just kind of jumped into this discussion of epoxides. All right, let's talk about how we prepare epoxides. All right, so if we have an epoxide, we'll take just our simplest 2-carbon epoxide. This can be prepared from an alkene. So we can convert alkenes into epoxides. And there's 2 ways to do it that are both perfectly equivalent. They'll always give you the same product. All right, the first is using this 2-step process where you use bromine and water, what's called a hydrohalogenation. And then you take that intermediate there and you treat it with a strong base like sodium hydroxide. Or I don't really know why, but they really like to instead use potassium hydroxide. And ethanol, in theory, any strong base. Okay, or using what's called a peroxy acid, such as MCPBA. We'll talk a little bit more about what that peroxy acid is here in a minute. All right, so for this first method here, we're going to discuss in a little bit more detail. We'll actually have a mechanism for that method. All right, so the first step of this reaction would have been a reaction that you would have learned about in the first semester. All right, if we start out with an alkene, we can react these with bromine. All right, and these form these weird intermediates here. My pi bond plays the role of a nucleophile attacking that bromine, but then the bromine attacks back with its pair of electrons, creating this cyclic bromonium ion. And now we have our now we have our second step, our water molecule. That's going to come along, and we'll see sort of a ring opening reaction. Oh, sorry, that has to kick that off as well. All right, we'll have one more step here. All right, see if you can't finish off our mechanism using just some base. Okay, sorry. I see what I did wrong. This bond actually breaks in that first step. My charges weren't working out here. Boom. There we go. And this creates what's called a halohydrin. All right, so then in our second step, we're going to take this halohydrin and we're going to treat it with this strong base. Right, so we have a strong base. What they do is they put it in a relatively non-polar solution, about as non-polar as you can get hydroxide to survive in, which is still pretty polar, ethanol, all right? But it makes it so that this reaction will then prefer this base event rather than any sort of substitution. So my hydroxide here under these conditions is going to act as a base and deprotonate that alcohol. All right, so I want everybody to take a second and to draw that missing intermediate. And then to see if you can't figure out how to finish this mechanism to create our epoxide, our cyclic ring. And we can note that in this process, we're going to have to kick off that bromide leaving group. Right, we get lazy sometimes and don't draw our inorganic product here, but for the sake of sort of keeping this all balanced, I'm going to include it over here so you can hopefully easier see what to do in this next step. So we can note we have our alkoxide intermediate, my deprotonated OH group. Okay, and now we need to do this next step here where we're going to create a new carbon-oxygen bond. And we need to remove this carbon-bromine bond right here. All right, so what we're going to have is this internal nucleophilic attack kicking off that bromide leaving group. All right, this will form my new bond. That's what that arrow's doing with this pair of electrons. And my bromide has now accepted that extra pair of electrons from that carbon-bromine bond to become my bromide ion. And so we see that after we get that halohydrin, we turn around and treat it with base, and we're left with our epoxide. Cool. All right, so that is a pretty, it works. I can tell you from having attempted in the lab, it's kind of a huge pain in the ass, to be honest, because to then isolate your epoxide afterwards is just not an easy feat. So if you got the money for it, the more preferable way to do it is using one of these peroxy acids here. All right, so what do I mean by a peroxy acid? All right, these peroxy acids all have this same general formula, COOOH. It looks very similar to a carboxylic acid, just with an extra oxygen. All right, so my structure here, just like a carboxylic acid, I have a carbonyl group bound to an oxygen, but it's not a hydroxyl oxygen. I now have this oxygen-oxygen single bond here. All right, different from my carboxylic acid, right, where I would just have a hydrogen on that carbonyl oxygen, or oxygen bound to my carbonyl carbon, rather. All right, so our peroxy acid has this oxygen-oxygen single bond with a hydrogen on the other side. All peroxides have that same oxygen-oxygen single bond. All right, so our peroxy acid, we're going to see this a few times in this course, and they always do something kind of weird. They're going to stick an oxygen between an existing carbon-carbon bond. All right, so if we take an alkene and we treat it with this peroxy acid, we will get our epoxide with that oxygen that's been inserted between that carbon-carbon pi bond. And a carboxylic acid. All right, so that same peroxy acid, just now minus that oxygen that was inserted between that carbon, those two carbons. All right, there's one that they love to use the most, presumably because it's nice and stable. You can keep it on the shelf for a while without having to worry about it deteriorating, called MCPBA. All right. We can just abbreviate it, but just to sort of note here, this is a peroxy acid where that peroxy group and that chloro group are meta to one another. We always just abbreviate it MCPBA, but it's meta-chloro-peroxybenzoic acid. All right, so we can see we have a chloro group and our peroxy acid group meta to one another. All right, but this is sort of the preferred method of converting alkenes to epoxides. All right, so what you'll see is your chemical equation, you have your alkene. Again, it just says MCPBA, and you know that that is a method of creating epoxides. All right, here's my chemical equation, how that's going to appear in there. Cool. All right, so we're starting out with alkenes. Well, we have alkenes, we know they have specific stereochemistries. So now we're going to have to discuss how stereochemistry is going to factor in to our epoxide reactions. So let's imagine we have two different alkenes with different stereochemistries. So here we have the E, here we have the Z, both of our 2-butene. We're going to treat these both with our MCPBA in order to create our epoxide. All right. Well, remember our alkene geometry. Our alkenes are flat. If we're going to add an oxygen to create our little triangle here, the oxygen's going to have to go on one side of that alkene. Those two bonds have to be pointed in the same direction. So I'm either going to be inserting my oxygen on the very top of this molecule or on the underside, but that's going to keep those same methyl groups locked in their positions, right? On this side, they're locked on opposite sides. Whereas on this side, they're on the same side, right? So we can call this our trans or cis alkene. Well, when we create our epoxide, we're going to have to maintain that or preserve that stereochemistry. All right, so when I draw my epoxide products here, I'm going to, for my trans alkene, draw my trans epoxide, where one of those methyl groups is pointed in one direction and the other one pointed in the other direction. All right, so then take a second and try to draw me the cis of our epoxide, starting with our cis 2-butene. Alright, so now I'm going to have to do my two methyl groups pointed on the same side. Whether you drew two wedges or two dashes, it doesn't matter. I'll always get a mixture of both of them. But importantly, you'll only get those two, not any ones where it's pointed on opposite sides, right? So both of these cis stereoisomers.
I have a question.
Yeah.
You had said I think it was for one of the previous chapters, you could just draw two straight bonds. Was that for the transformation or the cis when you're like?
So if you draw the straight lines, that means that I have a 50-50 mixture of both of these.
Okay.
So if this reaction wasn't stereospecific, then you could just draw straight lines. We wouldn't have to deal with dashes and wedges at all. That means that you got every possible stereoisomer with the straight lines. The reason why we're not allowed to do that is because these reactions are stereoselective. I won't get any of this one in this top reaction here. So now we do have to specify with dashes and wedges. All right, so this is going to have implications for when we go and do our next step as well, do our epoxide reaction. So let's just take one of these examples here. All right, and we're going to follow this up with one of our nucleophiles. We'll do that good hydrogen sulfide nucleophile. All right, so the reason why this is going to be important, and I've kind of tried to hammer this in with how we were drawing our products in the first place, is my nucleophile is going to have to attack. In this case, it's symmetric, so it doesn't matter which carbon I'm going to pick. I'm going to just draw it in blue here. It's going to attack this carbon. Well, it's not allowed to attack it from the same side as where that bond is that it's trying to break. It has to attack from the opposite side, right? What we call our backside attack. Right? Then we can see that ring opening reaction. Okay, so in a reaction such as this one, when we draw our products, all right, we have to indicate the proper stereochemistry of those products. We started out with a stereospecific reactant, thus we got to preserve our stereochemistry here. All right, so how am I going to draw this in here? Well, what's going to be on the orange carbon according to my mechanism? What functional group at the end? The oxygen, right? So on that orange carbon, I'm going to draw my oxygen, and I'm going to draw my nucleophile, my sulfur, on the opposite side, right? To show that there was that specific backside attack. So my oxygen from my epoxide is on top, my sulfur is on the bottom here, okay? We can finish out those functional groups. It's gonna be an OH group and an SH group. But now we have to fill in those methyl groups, and we need to make sure to preserve their stereochemistry. Well, my wedge is going to remain a wedge. All right, on my green carbon, I'm going to see the exact same thing. That methyl group didn't flip sides or anything like that. It just got moved up. So it remains a wedge on this side as well. All right, now let me show you a very common error that people make, and it's just not the same structure. All right, if I instead were to say, all right, my oxygen is on my orange carbon, and my sulfur is on my green carbon, but I draw them both on the same side, I keep my wedge, keep my wedge. This is not the same molecule. All right, you could go in there and assign RS stereochemistry and convince yourselves that these are two different molecules, and importantly, the one on the bottom is not what's produced in this reaction, right? So it's very important that when we start drawing our products, we start by putting our nucleophile on the opposite side of where that oxygen is. All right, if we do that correctly, then we just keep our wedges stay wedges, our dashes stay dashes, nothing crazy. Okay, if you try to put them on the same side, now you've drawn a different molecule. All right, so let's do another one here. We're gonna go from scratch. All right, so first you're going to take this alkene and treat it with MCPBA, and then you're going to treat it with one of our cyanide ion nucleophiles. All right. See if we'll break this into two steps. See if you can't first draw me our alkene with its correct stereochemistry, or I'm sorry, our epoxide with its correct stereochemistry, and then finally our product with its correct stereochemistry. Hold on, this is a crappy example. It's not it's just got more than one product here, so we're gonna make this a tertiary carbon over here. Boom. Sorry. Let's add one more methyl group onto that alkene. so step one, we want to start with that triangle. All right, start with your epoxide. We know this is going to be the product of this reaction. All right. Once we get that triangle, then we're going to fill in our carbons. If they're on the same side of that double bond, that means their bonds must match. All right, so what do I mean by that? My two methyl groups over here are on the same side of that carbon-carbon double bond. So I need to make them either both wedges or both dashes. Doesn't matter which one you want to pick. They just got to be consistent. All right, so these are my two methyl groups. They were on the same side, so they must match. All right, that means that that other carbon, my ethyl group, it's going to have to be on the opposite. A wedged, a dashed bond. All right, so now we've created our epoxide, our stereo-specific epoxide. Okay, we're gonna have way too many colors going on, so I'm gonna get rid of these. All right, so now let's take our second step here. All right, according to my nucleophile formula here, is this an acidic nucleophile or a basic nucleophile? So this one's a basic nucleophile. So I gotta look, which carbon is it going to attack? My orange secondary or my green tertiary. Yeah, so it's going to be the more accessible one. The other thing about these cyanide ions is we write their formula a little bit misleading, right? In that cyanide ion, where is that negative charge living? On the carbon, right? So importantly, this is kind of how we write a cyanide ion. Our shorthand, we want to be good though. Our Lewis structure here has this carbon-nitrogen triple bond where the negative charge, they both have lone pairs, but the negative charge is on that carbon. All right, so I'm not going to do the full mechanism, but I am going to illustrate how we have this backside attack and our ring opening. So when I draw my epoxide here, now I'm going to draw, again, starting with those same two carbons, right? My tertiary carbon is what held on to that oxygen, whereas that secondary carbon is what my nucleophile was added to. Be good and draw that triple bond linear. All right, so here we need to draw our product with our OH and our nucleophile on opposite sides. And now we're going to fill in our carbons, maintaining that stereochemistry. Meaning if it's on a wedge on the left, it needs to be on a wedge on the right. So that methyl group, it didn't switch sides, it just got kicked up, but it's still pointing out of the page towards me. All right, likewise on that green carbon, that methyl group still pointed towards me, and that ethyl group pointed into the board. All right, but again, you want to make sure that you have your nucleophile and hydroxyl group on opposite sides. Cool, and so then the last thing to consider here was those conditions. Let's take this exact same epoxide, but now we're going to react it with one of our acidic condition nucleophiles. We can use one of those weak nucleophiles, because under acidic conditions it makes that epoxide an even better electrophile. All right, so everybody take a second and give me my product here. So now that nucleophile is going to attack that more substituted carbon. So I'll have my hydroxyl group from my water pointed down, and my hydroxyl group from my epoxide pointed up. I'm going to draw in my carbons, but maintain their stereochemistry. On the carbon that got attacked, my wedges are still wedges and my dashes are still dashes. They're just now pointed in that different direction. Cool. All right, so, and one more thing, I'm kind of being lazy here. At each step of the way, when we created our epoxide, we should really be good and say, and it's an enantiomer, and our product, and it's an enantiomer. However, on your homework and on your exam, I'm cool with you just giving me one of those two enantiomers, right? That shows me that you're following your stereochemistry. So if you gave me this answer, that would be correct, or if you flipped all of your dashes to wedges and wedges to dashes, that's also perfectly acceptable. All right, that's its enantiomer. Cool. All right, the last thing is if we instead started out with a ringed structure, there's kind of an even more convenient way to draw our products here. So let's say we started out with cyclohexene. For the sake of fun, we'll do our other synthesis of epoxide method here. All right, well, I again got to show that this epoxide is on the same side of this ring, but here it's a little bit easier to do by showing my triangle using my dashes and wedges. All right, then if we followed this up with some nucleophile, let's do this amide ion here. It again has to attack from the opposite side. which means that my two functional groups will be pointed on opposite sides of the ring. Now my nucleophile that got attached is pointed into the page. It got attached from the back side. My oxygen is still pointed out of the page towards me. All right, so this would be how we show stereochem for ringed epoxides. All right, and importantly here, right, the main feature is our nucleophile and our hydroxyl groups are on opposite sides of the ring, right, because of that backside attack of our nucleophile. Oops. Go. All right, we will kind of just rewind and start doing some reviews starting on Friday. Yeah.
I wasn't sure if you were recording these ones. I was just wondering because I think I missed class again.
Yeah, they're recorded. The first one's posted. The one from